what we had left off in the last class. VH loop, yes. So we were looking at open circuit test and short circuit test. If you may recall, we had drawn the equivalent circuit, overall equivalent circuit of the transformer. We also drew the phasor diagram. We said this is RC, this is XM, and here is V1, what we are applying. So now this is R2 dash, this is X2 dash, and then this is what is our load, which we are calling as ZL dash, right? We wanted to first of all determine all the parameters of this equivalent circuit, which actually can be done by two tests. We said that actually loading the transformer is going to be difficult because we would end up wasting a huge amount of power, and it will be very, very difficult for us to actually find the load which can withstand the rated current or rated power. That's the reason why we would like to determine the parameters, if it is possible, by creating situations like applying rated voltage without really passing rated current, and the second situation, applying or passing rated current, whereas applying only a fraction of the rated voltage. So we are not really loading the transformer to the fullest extent, neither by the current or nor by the voltage. That's what we are trying to do. So in this case, we initially talked about OC test. So in OC test, what we said was that we are going to have the transformer connected through a wattmeter, right, and an ammeter. So this is actually applying the voltage to the winding, which will be the low voltage winding. We are going to call this as LV winding, whereas the winding which is actually open circuited, that is going to be HV winding, right? So now we will also measure the voltage what is applied here. So we are going to call this voltage as V1. Whatever is applied is V1. Okay. So what I get as the reading will be V1, I1 and maybe W1. Rather, I named these as V0, I0 and W0 to specify that this is no load condition. So I am going to show this as I0 and this as W0, and of course the voltage applied here is rated voltage. And it may be very difficult for me to find the rated voltage if I am choosing the high voltage winding which is to be excited. That's the reason I am trying to conduct this test by applying the voltage on the low voltage side, just for logistics reason, right? So this is what we are doing, and then we got basically W0 equal to V0 I0 cos phi naught. So I should be able to get exactly what is cos phi naught or the no load power factor, from which, and from the phasor diagram we drew earlier, if this is V0, I am going to have actually this as IC and this as IM, and the addition of these two I am going to get as I0. So I am looking at IC as I0 cos phi naught, and we can say V0 by IC is equal to RC. Okay, and I am going to have similarly IM, or the magnetizing current, is going to be I0 sin phi naught. So I am going to write V0 by IM is equal to Xm, right? So I have got the parameters which are corresponding to the parallel parameters, that is whatever is my RC and Xm, that's it. These two are determined based on my no load test or open circuit test. I am not loading the transformer, I have kept the secondary on open circuit. That's the reason this is known as no load test or open circuit test. Incidentally, the same circuit can be used for determining VH loop, but with a little bit of modification. So we are actually looking at the transformer under open circuit condition. So I am still showing the transformer under open circuit. The secondary is on open circuit. Okay. The primary is applied with the normal magnetizing current because it is on open circuit. Let me put a small resistance in series with the primary winding so that the drop in the series resistance will be whatever the series resistance, let me call that as RS. So RS multiplied by IM, whatever is the magnetizing current or the no load current, that will be the drop across the series resistance. So if I may call this as RS, I am going to look at the drop across this as I0 times RS. That is going to be the drop. So what I get there is a voltage. The voltage is actually giving me the no load current multiplied by the series resistance. And this series resistance is known to me. Let us say I am able to measure this with the help of, multimeter or whatever, and I know the value, so I can say I0 times RS is the series resistance. Fine? I0 times RS is the drop. Now this is connected to the primary side, and on the secondary side, I would like to get a measure of the flux, if I can. Because if I get the flux and if I get the magnetizing current or the no load current, I am going to neglect the core loss component of current. I am assuming that the entire current that is flowing is approximately the magnetizing current. Okay? Because I will not be able to segregate the two components of current, physically or experimentally. I can do it theoretically, but I cannot do it actually physically or experimentally. So what I am assuming is the no load current that is passing through the transformer is same as that of the magnetizing current. Approximation. That's what I am doing. Now, this voltage drop I0 times RS will tell me what is actually the magnetizing current quantity. So this will obviously go to the x-axis of the plotting of B versus H. If I want to plot, I will give this to the x-axis or x-plates of the CRO. Right? That's what we were doing. If you may recall, this will go to the x-plates of the CRO. So I will put the CRO in XY plot mode. Now what I want is the flux. The flux has to go to the Y plate. So to actually give the flux value directly, rather than that, I can say normally d phi by dt is voltage. This we know, N times d phi by dt. Maybe, let me write that like that. So I can indirectly say if I want flux, I should be able to integrate the voltage. If I integrate the voltage, I should be able to get actually whatever is my flux. So instead of getting the voltage integrated, what I am going to do is to connect first of all a resistance and put a capacitor here. Let's say if I do it, what is going to happen? Now, the current, the voltage here is V2. Let me say it is V2. I am applying some voltage V1 on the primary side. V2 is induced on the secondary side. And it is on no load, so hardly there is any drop. The entire voltage is coming up. Okay? This resistance is going to be a very, very large value. Let me call that as RL. Doesn't matter. This RL is going to be a very, very large value. What I mean by large, again large and small are relative. If I say it is a 2.2 kVA, 220 by 110 volts transformer, repeatedly whatever we had used earlier, I am just using it again. 5.5 ohm is my normal secondary resistance if I want the secondary current to be at rated value. Right? But instead of 5.5 ohm, if I use maybe 200 ohms or 300 ohms, I would call that as a very high resistance compared to the nominal resistance. So I am going to look at a resistance which is way too high as compared to the nominal or rated resistance that I may connect such that the rated current flows through the transformer. So RL is going to be much higher than the nominal rated resistance of the transformer. Not resistance of the winding of the transformer, I am talking about resistance which I will connect as the load resistance normally. So instead of 5.5 ohm, I may end up connecting 200-300 ohms. Very large resistance. Now I have a capacitance also. So if I try to look at what is the current that is flowing here, okay, let me call this as some I20 because this is still considered to be no load. Are you getting my point? If I had connected 5.5 ohm, I would have gotten maybe 20 amperes. Now that I am connecting 300 ohms, the current will be negligible, literally. So I am calling that as I20 because it is at almost zero load. So I20 is going to be V2 divided by RL plus, or I should say minus, it should not be plus, it should be minus JXC. If I choose the capacitance in such a way that RL is much higher than XC, I can definitely choose a capacitance. It is 1 by omega C after all. So if I try to look at the overall impedance, it will be RL square plus XC square root. If XC is really small, you know, I can say RL square plus XC square root is approximately equal to RL itself. So I'm going to choose a capacitance in such a way that this impedance is almost equal to RL itself. So I'm going to have this as my I20. So I should say that C is chosen such that RL is much higher than XC. Right? So because of which I can say the current is mainly dependent upon RL only, nothing else. Okay? So I can substitute this here. If I try to look at what is the current that is flowing here, please remember CRO terminals what I have is like voltmeter terminals. So obviously there is hardly any current going into the CRO. So the entire current that is flowing here has to flow only through the capacitance. So I am having the current to be V2 by RL. So the current through the capacitor will also be V2 by RL. But the voltage across the capacitance will be 1 by C integral I dt. That is what is the voltage across the capacitance, which will be 1 by C multiplied by V2 divided by RL dt. Am I right? So we are integrating the voltage indirectly by passing the current through a capacitor. So what I am getting as the capacitor voltage, which I am plotting in the y-axis of the CRO, is a measure of flux. Of course, it has some multiplication factor like 1 by RC or whatever. I do have definitely a multiplication factor, no doubt. But it is a measure of flux. So what actually I am going to get across the Y plate. So this is going to go across the Y plate of CRO. This terminal will be connected to Y plate. That will go to the Y plate of CRO. So what I am getting across the Y plate of the CRO, I can write it as Y plate of CRO gets basically integral of V2 divided by RL and 1 by C dt. This is what is coming, which is actually equal to 5 divided by N, right? Because N d phi by dt is voltage. That's what we said. So obviously if I am only looking at voltage, it is voltage divided by N will be d phi by dt. So phi will be voltage divided by N integrated. Right? So I am getting a measure of flux. I'm not saying it is exactly flux per unit area, flux per whatever, unit turn. I'm not saying that at all. I'm basically saying that I'm getting a measure of flux. As simple as that. That's all. So what we do in the BH loop experiment is to send this to X plate and send this to Y plate. So this goes to Y plate and this goes to X plate. So what I am getting in the X plate is not really H and not even IM in ampere. It is rather IM multiplied by whatever is the series resistance I have got. That's the reason why if I want really in amperes, whatever is the magnetizing current, I have to divide it by RS. RS I have measured, so it's not a big deal. So what I am getting is not directly IM in amperes. I am rather getting IM multiplied by RS in volts. So ultimately I have to scale everything to get the hysteresis loss. So this is essentially the principle behind BH loop, right? But I hope you understand the principle behind the experiment. One word of caution in this experiment. When I connect this to H plate and connect this to Y plate, please understand that the CRO will have, in X plate there will be 2 terminals, in Y plate also there will be 2 terminals. So one of them will be grounded and the other terminal will be given to the signal, or vice versa. We don't know, right? It's after all AC. So I don't even know whether I'm going to ground this terminal or this terminal. I don't know. So if I by chance ground this terminal, for example, whereas this terminal of the transformer is grounded, probably, right? It is as good as short circuiting that particular complete, the connection itself. The primary is short circuited. So I don't want that to happen. That's the reason why the CRO ground is anyway connected to the main ground of the laboratory. I can't help it. That is done already. I can't do anything. That's the reason why we use an isolation transformer here. There will be an isolation transformer at this point. The isolation transformer, all it does is, it will be a 1:1 transformer. So what I will have is an isolation transformer in the input side, like this, and I'm going to connect this to the supply. So I know for sure that probably this side is grounded. It doesn't matter. From here I will connect it to RS and whatever I have to do, and then I will connect it to this transformer. So this is the transformer under test. So this transformer will be transformer under test, whereas this transformer will be isolation transformer. Got it? So now, after all, the transformer under test and the transformer which is connected to the other side, they are not connected together. In terms of electrically, they are not connected together. The primary and secondary of the isolation transformer are isolated from each other. There is no connection directly between the ground of the primary of the isolation transformer and secondary of the isolation transformer. Now I don't have to worry. All the grounds are separate. Right? So I don't have to worry that something is really going wrong with the entire connection. That will not happen. So normally BH loop experiment will never be conducted without an isolation transformer. The isolation transformer is only meant for making sure that nothing is short circuited, inadvertently, without knowing some ground is connected to some other ground, and then you will just see a Diwali. You don't want that to happen. As simple as that. That's the reason. Right? Got it? So much so for the open circuit test and BH loop of the transformer. So let us try to look at the short circuit test. Yes. Auto transformer cannot be used as an isolation transformer. Auto transformer cannot be used as an isolation transformer because it has only one winding. The primary and secondary are not isolated. So if I have a ground for primary, it is very much the ground for secondary also. I am not differentiating between them. So auto transformer cannot be used as an isolation transformer. No way. Right. So let us try to look at the short circuit test. So in the short circuit test, as the name indicates, I am having the transformer here and I am going to short circuit the secondary. The secondary normally is chosen to be the low voltage winding in this case. So I would try to apply the power supply from the high voltage side, whereas this is LV. Why so? High voltage winding will have lower current, obviously. I want to pass rated current, right? 220 by 110 volts. We got 20 amperes as the current on the low voltage side. And on the high voltage side, it was only 10 ampere. So high voltage side, if I energize and if I have to pass rated current, then I don't have to worry so much because I don't have to look for very high current value source. I don't have to look for that. So I would always try to energize the high voltage side when I am conducting the short circuit test. But I have to keep an eye on how much is the current that is flowing because I don't want to exceed whatever is the rated current value. So I have to continuously keep an eye on the ammeter. So normally I will connect an ammeter in series in this case also. And of course I would like to measure the power, so I would also connect the wattmeter very clearly. Okay? See, if I am talking about again 2.2 kVA, 220 volts by 110 volts transformer, corresponding to 220 volts, I have only 10 ampere as the rated current. Whereas for this, I have to look for a 20 ampere source if I want to push rated current through the winding. Right? I am connecting the source on the HV side, so my source has to pump in only 10 ampere, not 20 ampere. So I am always looking at lesser amount of value being applied, whether it is current or voltage, from my source. So in this case, I am not going to apply rated voltage anyway. I am going to apply only rated current. So where is the less value of rated current present? That is only present in the high voltage side. So I am using the high voltage side for energizing. Right? Now, we had the equivalent circuit of the transformer as R1, X1, and of course R2 dash and X2 dash. Let me forget about the parallel values, doesn't matter. Now here I have short circuited. This is the short circuit. I have completely short circuited this portion, which means the impedance that is limiting the current in the series path is R1 plus R2 dash plus J times X1 plus X2 dash. That's all is limiting the current. And if you look at R1 plus R2 dash, I told you that they will be very, very small because I'm not going to really let a huge amount of voltage drop within the transformer. I want to design the transformer well so that it doesn't eat away all the voltage that I am applying. Right? So R1 plus R2 dash is also going to be small and there is hardly any leakage because there is not much of air gap. So the leakage reactances are also going to be very, very small. So overall, the drop that is taking place here, I would say the drop is generally small unless I deliberately design a bad transformer, which is generally not done. So I would see that to pass rated current, now I want to pass only rated current. This is I rated. So in this case it is 10 ampere, for example. So I will have R1 plus R2 dash plus J into X1 plus X2 dash multiplied by I rated. This is actually whatever is the voltage that I have to apply on short circuit. Under short circuit condition, if I want to pass only rated current through the primary winding, I am reading it continuously and I don't want that to exceed the rated value. The impedance is R1 plus R2 dash plus J into X1 plus X2 dash. So that multiplied by rated current should have been the applied voltage from the primary side, so that it will only actually, put the rated value of current passing through the transformer windings. Whether I look at the primary or secondary, if I limit the current to rated value, both of them will be limited to rated value. Okay? So I am going to have essentially the voltage applied during the short circuit test to be much, much lower than the rated value of voltage. So under short circuit test, whatever is the voltage I apply, indirectly it gives me an indication of what are the internal impedances of the winding of the transformer. It gives me a feel for what is R1 plus R2 dash, what is X1 plus X2 dash. So if the voltage applied during short circuit test is only 10% of the rated value, that means the voltage drop that is taking place within the transformer winding is only 10% of the rated voltage. If it is 5%, that means I have even lesser amount of impedance internally within the transformer. So the voltage drop becomes less and less. Yeah. It's not zero, it is very small. See, if I am talking about RC, I said basically that RC is, taken to be generally in such a way that it balances whatever is the hysteresis and eddy current loss. And I am going to have very low hysteresis and eddy current loss in a transformer. Hysteresis loss I don't have much control, but eddy current loss I am decreasing as much as possible. If I am decreasing the eddy current losses and hysteresis losses quite a bit, that means IC is going to be really, really small. Right? If IC is small, RC has to be quite a lot. IC square RC. Please note that IC has more influence on the losses than RC itself, because RC power 1 whereas IC power 2. So IC I want to minimize. If I want to minimize IC, RC has to be increased quite a bit. So RC normally in a transformer will be like 1000 ohms, maybe more. Okay? So the better the design of the transformer, RC value will almost tend to infinity. It's not infinity. Compared to the winding resistance, it will be very, very high. That's all I'm trying to get at. So this will be some thousands of ohms. Similarly, if I look at XM, XM is also essentially talking about what is the mutual inductance between the primary and secondary. In one sense, because that is the one which is talking about the common flux that is existing between primary and secondary. So if I don't have much of air gap, obviously the coupling between the primary and secondary has to be pretty much intact. So I am looking at this, actually this XM value is an index of how permeable the core is. Right? So if the permeability of the core is pretty good, XM will be a very high value. So higher the value of XM and higher the value of RC, I would say the transformer is getting closer and closer to the ideal transformer. So normally this is IC and this is IM, which put together actually make up for my no load current, and the no load current is less than 5%. So I really do not have to take that into consideration. When 10 ampere is flowing through the primary winding, this may be 0.04 or something like that. So 0.4 or 0.3 or something, I don't have to worry so much to take that into account. That's the reason why I'm neglecting it. Okay? So this VSC what I apply normally done through, it will be done through an auto transformer. So I'm going to show the auto transformer here, and this is applied by only influencing or applying the voltage with respect to only a fraction of the total turns available in the total auto transformer winding. So this is where I apply the 220 volts or 230 volts. So I'm going to apply V rated probably at this point. Rated voltage is applied here. From there is a variac or auto transformer. From the auto transformer, this is the variable jockey point which is going to probably be put at very minimum number of turns. So what I will do is slowly increase the voltage applied by increasing the jockey position of the transformer, or rotate. I have to rotate it and then make sure that I don't exceed the rated current. So I can't really, directly apply this here. So let me show this here again. This will be connected to a variac like this. So the earth point, please note, is the same. So variac cannot isolate. It cannot isolate between the primary of the transformer under test and the power supply. It's not isolating. It is actually the same earth between both of them. Okay. So I have to have the power supply connected here. That is where 220 volts is connected. Yes.
By adjusting jockey, we can manage the voltage.
Yes.
How we can manage the current here?
If you are applying only less amount of voltage, where will the current come from? It cannot. See, you have an ammeter connected. So this ammeter, you have to keep an eagle eye on that continuously. Up.
Like that we do in the open circuit test.
You apply rated voltage. No, that is in BH loop. You will not have an isolation transformer in all the no load tests, not at all. That's why I said that is another little diversion I had taken. Let me go back to the previous slide. Right? This is actually our no load test. Okay? Oh, it didn't go. Okay. So this is actually our no load test. Right? This is actually the BH loop. I think this is the no load test. So this is the open circuit test where I have not shown any isolation transformer. What I could have shown is directly apply it through a variac, and the variac in all probability will be connected to the top point. No isolation. Open circuit test does not require an isolation. But if I am plotting a BH loop, because I am connecting the power components directly to the CRO, and CRO is meant only for electronic components, not meant for power components. I am mingling the two. I better take precautions.
I'm saying that in the short circuit test, can't we use isolation transformer for managing the current here?
You can use, but why would you like to do it? Because isolation transformers are costlier. Auto transformers are less costly. And you don't need to separate the earth. Unless you have a requirement to separate the earths, you generally do not use an isolation transformer. In the laboratory, we can do anything. But if I try to go to an industry and ask for an isolation transformer for this kind of a job, they'll kick me out. Right? So I have to see what is done most economically. Got it? Okay. So let us look at now the short circuit test calculations. So I am going to have VSC, ISC and WSC. WSC will give me only the real power quantity, which will be very clearly ISC square multiplied by R1 plus R2 dash. Only two resistances are there and only they can dissipate real power. So what I get actually as WSC will be ISC square multiplied by R1 plus R2 dash. Right? And from here I should be able to get what is the value of R1 and R2 dash. Generally, it is very difficult to separate out R1 and R2 dash. Similarly, it is very difficult to separate out X1 and X2 dash. Most of the time, we take it as what we get as the total resistance divided by 2, we will take as R1. Similarly, total resistance divided by 2, we will take it as R2 dash, which is okay for all practical purposes. Right? If I had measured the resistance already of the primary winding right at the inception stage, then it is different. Otherwise, R1 and R2 dash, similarly X1 and X2 dash, it would be very difficult to segregate. I would only get the total value, so I may call this as R equivalent. I may call this as R equivalent. Similarly, I can say that VSC, ISC, cos phi SC equal to WSC, from which I know what is cos phi SC. Once I have cos phi SC, I can directly get the impedance from VSC and ISC. It's a series circuit, mind you, unlike open circuit test. In open circuit test, it was a parallel equivalent circuit. So we were trying to look at the currents being divided. Here the voltage is getting divided between R and X, right? So I can say basically in this case as ZSC VSC by ISC. So I can say ZSC sin phi SC will be equal to X1 plus X2 dash, which I may call as X equivalent. Right? So I have got X equivalent and R equivalent of my transformer windings, which will account for the series parameters in the equivalent circuit. Once I have these, that is R equivalent, X equivalent and the no load losses, I should be able to assess the performance of the transformer under different load conditions, whatever I imagine. Not a problem, because I know the parameters of the transformer, right? If I had to load the transformer, the same 220 by 110 2.2 kVA transformer, how much of power I would have wasted? Because I should load it probably for first 2200 watts, then I have to do it for maybe 1100 watts, 1000 watts and so on and so forth, and then I'll have to see how I am getting the voltage at the terminal and what is the kind of efficiency or the wattmeter reading that I am getting, right? So it would definitely entail a huge amount of loss, right, which actually I would be dissipating in the external resistance. And at least if it's 2.2 kVA, I can manage the show. If it is 400 megawatt, I really had it. So I cannot really expect to be loading a 400 MVA transformer with the help of, a proper resistance and things like that. Right. So now that we have seen these two tests, let us try to now look at the two performance parameters of the transformer. One is efficiency and the next one is voltage regulation. Right? So if I am looking at efficiency, right, the efficiency is defined as in terms of power, real power. So I have to say output power divided by input power. This is what is efficiency. right? Output power, maybe I am giving it to an induction motor, I am giving it to a resistive load, I am giving it to probably a heating unit. Maybe I am giving it to whatever apparatus I am having. I may be having some way of measuring it, right? So I may be able to measure the output power, or I may say that I want an output power of maybe 250 watts from this transformer. So in which case, how much should I apply from the input side? I should have a fairly good idea. That's the reason why generally the parameter estimation of a transformer becomes extremely important. That tells you indirectly, internally, how much the transformer is going to swallow and how much will you get at the output. So if I want so much of power output from the transformer, really how much should I be supplying? This is one thing. Second thing is, if I know that out of a 250 watt output of a transformer, maybe it is going to dissipate 20 watts. To that extent, the transformer will get heated up. So, am I providing adequate cooling for the transformer? Will the transformer get overheated? Because of which, the surrounding components will also get overheated. And ultimately, it will result in a failure, right? For example, in your PC, you have that SMPS. That SMPS will always have a transformer inside. That transformer probably is going to carry only about 300 watts of power, nothing more than that. But out of 300 watts of power, maybe it will be dissipating 20-25 watts, and it is a pretty constrained space. There is hardly any space available. So, you might have to make sure that adequate cooling is being done. So, if adequate cooling or circulation of air is not available, I might have to fit a small fan, right? That will consume more amount of electricity, that is different. But I have to make sure that nothing fails, right? So, we would say that the efficiency estimation becomes extremely important from these two viewpoints. How much is the input power I have to give, and how much of the cooling that I have to make sure that is available for the apparatus that I'm using, right? So, I can say this as output, if I am able to measure, output power divided by output power plus losses, right? So, what are the two losses? The losses will correspond to copper loss, which is actually I square R loss, nothing else. So, I have to write this as I square times R equivalent, because I am rather putting together R1 and R2 dash, right? I may not be a constant. Are you getting my point? Depending upon how much is the resistance I have connected on the secondary side. If I connect 5.5 ohms in the 2.2 kVA transformer, it will be supplying rated power of 2.2 kVA. If I connect 10 ohms, then correspondingly I will have 11 amperes only instead of 20 amperes. So the current is a variable one depending upon what kind of load I have connected, right? So this copper losses are also known as, the variable losses. These are variable losses. They are not constant loss. This is known as variable loss. Right? The second kind of loss I have is iron loss or constant loss, which we already saw that is corresponding to IC square RC if I try to say it in terms of equivalent circuit. I can say that also that this will be equal to hysteresis loss plus eddy current loss, or I can also say this is W0, what I got as the no load circuit. When I did no load test, I got some W0. I applied rated voltage at rated frequency, so hopefully the flux is at rated value. If the flux is at rated value, I should be able to get whatever is the loss as the iron loss. So this is actually the constant loss. right? So in the next class, we will try to look at the actual efficiency expression under variable load condition. We will derive the condition for maximum efficiency. One particular point I had forgotten, which I have to mention in the next class, as to why the wattmeter reading in no load test represents only iron losses. Why the wattmeter reading in the short circuit test represents only I square R losses or copper losses. Why not the other way around? Okay, thank you.